Hi everyone, I'm Davey, and today we're going to be talking about how to use methods from multivariable calculus to find the area of part of a surface in 3 dimensions. Now, there is also a way to do this kind of problem using methods from single variable calculus, but that method, the methods in single variable calculus work only if the surface is a surface of revolution, meaning it can be formed by taking some curve and rotating it all the way or part of the way around some axis, tracing out a surface. This is, in fact, the case for the problem here, but the method I'm going to outline uses tools from multivariable calculus is, in fact, much more general, and I think easier to learn and apply. Of course, if you don't know the concepts of partial derivatives and double integrals yet, it may be hard to follow, but I think that I give enough intuition for how these concepts work that this video can also serve as an introduction to those concepts. You won't understand why those concepts were developed necessarily, or have rigorous understanding of why they work, but hopefully you will at least be able to understand them enough to apply them to problems like this, even if you haven't encountered them before. Okay, so what is the specific problem here? What surface are we trying to find the area of? Well, the surface is defined as a portion of the paraboloid z equals 2 plus x squared plus y squared that lies over a certain region R of the xy plane. Now, how do I know that z equals 2 plus x squared plus y squared is a paraboloid? Well, x squared plus y squared can also be written as r squared, where r is the distance from the point xy to the origin. This comes directly from the Pythagorean theorem. So we can write this equation as z equals 2 plus r squared. The height of the surface above any point is 2 plus its distance squared from the origin. From that distance squared comes the fact that any cross-section of this paraboloid is in fact just a parabola, any vertical cross-section that is. So if I take any vertical plane through the origin and slice through this surface, I'm going to get a parabola. Because within that plane, as I let the footprint in the xy plane go out from the origin, the height is simply given by 2 plus the square distance out from the origin. So within this plane, the equation for the surface is the dependent variable, that is the height, is equal to 2 plus the distance squared along the axis in the cross-section plane, which gives you a parabola. Now, what is the region R in the xy plane, the footprint of the part S of the surface, whose area we're interested in, look like? Well, R is bounded by 4 things. First, it's bounded by 2 lines, y equals x, which is the line at 45 degrees, both from the x-axis and the y-axis, passing it through the first quadrant, and the line x equals 0, which is simply the y-axis. The other 2 bounding curves of the region R are the circles x squared plus y squared equals 2 and x squared plus y squared equals 4. Remember, because of the Pythagorean theorem and the fact that it involves squares on all 3 variables, x squared plus y squared equals 2 is actually the circle of radius square root of 2. X squared plus y squared equals r squared. Similarly, x squared plus y squared equals 4 is actually the circle of radius 2, which is the square root of 4. So these are our regions R and S. We don't actually need to know what R and S look like in order to do the problem, but in general with geometry problems, it's good to draw a sketch of what you're talking about first in order to gain intuition. Sometimes you may find surprising patterns that may make your life easier. For example, in this case, you may not have realized that z equals 2 plus x squared plus y squared was a surface of revolution, but after trying to draw it, perhaps you would have realized that, and then realized you could have applied the single variable calculus surface of revolution method to this problem. In fact, we're going to use a different method, but that's just an example of how you can gain insight into how to approach a problem from drawing it. In this case, with our method, it's not really going to help us, but it's just a good habit to get into. Okay, so what is the formula that we're going to apply to find the area of this region S of the paraboloid? Well, the general formula says that whenever you're trying to find the area of a surface defined by some function z of x and y above some region r in the xy plane, then what you want to do is integrate the square root of 1 plus the sum of the partial derivative squared of the surface of z over the region r. I'll explain how a double integral works in a second. Essentially, it's a two-variable analog of the single integral. Whereas with a single integral, you're integrating over some interval, some one-dimensional region. With a two-variable integral, you're integrating not just a function of one variable, but a function of two variables. And you're integrating over a two-dimensional region, a piece of the xy plane, rather than simply a one-dimensional interval. And with partial derivatives, you're considering a function of two variables instead of a function of one variable, just like with double integrals. And whereas with double integrals, you turn your consideration from a one-dimensional region to a two-dimensional region, with partial derivatives, you're concerned with finding how much of the function is determined by each variable, how much of the change in the function is determined by each variable. So when I say partial z, partial x, what I mean is how much does z change for each change in x holding y constant. Similarly, when I ask for partial z over partial y, what I mean is how much does z change for each change in y holding x constant. Essentially then, partial z over partial x is the derivative of z with respect to x if you consider z as a function only of x and treat y as just a constant. So to get these partial derivatives, what you do in practice is you ignore all the variables, any other variables that aren't present in the denominator, any other independent variables, that is, if they're by themselves. And if they're combined with other terms, you treat them as constant multipliers, like 2 or pi. We'll see how that plays out in a minute, but for now, that's how partial derivatives and double integrals essentially work. So let's try applying this formula to our problem here. The first step is to deal with the partial derivatives, figuring out what they are for a specific surface z. Well, again, here's the equation of z. To find the derivative of this function with respect to x, we pretend it is a function only of x, treating y as a constant. The first term, 2, certainly has no derivative with respect to x. The second term, x squared, has derivative 2x with respect to x, just as is the case in single variable calculus. The third term, y squared, is the term for which our assumption that y is not changing is crucial. Y squared has no partial derivative with respect to x, because the partial derivative with respect to x is defined as how much a function changes if y is held constant and x is changing. By definition, if y is held constant, y squared does not change at all. It is also a constant, as a function of a constant. Therefore, the partial derivative of z with respect to x is just 2x. The other two terms contribute no x partial derivative. They don't depend on x. Similarly, the partial derivative of z with respect to y is 2y. After all, z is symmetric with respect to the variables x and y. Substituting those into the equation, we get the second line. 1 plus 4 x squared plus y squared is the new argument of the square root. Now, we now have to calculate an integral over a two-dimensional region R. Whereas there's really only one way to give coordinates in one dimension, namely we define a coordinate x that simply measures the value of each point as a real number. In two dimensions, there are various systems. There are the familiar Cartesian coordinates, but another system that is often very useful in problems involving structures with rotational symmetry about the origin, which we have here, as we have both circles, which certainly have rotational symmetry, and lines which pick out certain angles and are related to rotation also in a natural way. For these reasons, we want to apply polar coordinates in this problem. If you recall, polar coordinates are coordinates r theta in the standard notation as opposed to x and y that, like x and y, can describe any point in the plane. Where r is the distance of the point from the origin, so r is at least 0, and theta is the angle of a point counterclockwise from the positive x-axis. So for instance, if we draw the plane like this, the origin has r equals 0, and each circle around the origin has a constant value of r, which increases with the radius of the circle. In fact, it is the radius of the circle. So the unit circle of radius 1 has r equals 1. The circle of radius 2 has r equals 2, and so on. Theta is constant along rays starting at the origin. Every point along this ray has the 45-degree line y equals x, has theta equals pi over 4, which is half of the angle pi over 2 corresponding to the positive part of the y-axis. And this is because all these points are simply up at the same angle up from the positive x-axis. So sets of points of constant theta look like rays, sets of points of constant r look like circles, and for any point we can determine its coordinates by r theta by seeing which circle around the origin it lies on, and then on that circle, which of the many rays through the origin it lies on. The only exception is the origin itself, since all the rays pass through it. The theta coordinate of the origin is undefined, but as the origin is just a single point, this is never an issue when we're trying to calculate integrals. The values of functions at single points do not affect integrals. Okay, so if we're using polar coordinates here, then how can we write this integral in polar coordinates? Well, we need to do two things. We need to write the function we're integrating, root 1 plus 4x squared plus y squared, in terms of not xy, but in terms of the polar coordinates r and theta. And we need to write this differential here, dA, also in terms of r and theta. When we're multiplying by an infinitesimal area element, we have to express that element in terms of an infinitesimal change in r, dr, and an infinitesimal change in theta, d theta. It turns out that simple geometrical arguments give that dA should be taken to be r times dr times d theta. Now, this is not something we can justify quickly, but we can at least justify why an extra thing appears, an extra factor appears here, whereas using Cartesian coordinates, we would simply write dx dy. In polar coordinates, we cannot just write dr d theta. Dx dy gives you an area element, but dr d theta does not. And one reason dr d theta can't give you an area element is because it has the wrong units. Whereas dx dy has units of length times length, dr d theta has units of length times angle, and angles, for reasons that are sort of technical, technically don't have units at all. Yes, you can measure them in radians or degrees, but this formula for the differential r dr d theta actually only works when angles are measured in degrees. Otherwise, you'd have an extra constant factor. And when angles are measured in degrees, it actually will make sense to treat them as unitless. The upshot is there's only one factor of length in dr d theta, whereas dx dy has two factors of length. You need two factors of length to get something with units of area. So this extra factor of r gives you the other factor with units of length to give you units of area in this factor, which we need to happen because this is supposed to represent an infinitesimal piece of area. Okay, but assuming you believe that, the other factor is easier to write, the integrand itself. X squared plus y squared we know is equal to r squared. This is one of the basic relations of polar coordinates. R is the distance between x and y in the origin, and the Pythagorean theorem then equates x squared plus y squared and r squared. So we can rewrite this integrand as root 1 plus 4r squared, yielding that the double integral we have to calculate is the double integral of the function root 1 plus 4r squared times r with respect to the variables r and theta over the region big R. Now, what is the region big R in terms of the coordinates r and theta? Well, theta ranges from pi over 4 to pi over 2, as you can see in this diagram. Recall that the region R lies between the angles y equals x and x equals 0. And it includes all area between radii root 2 and 2 for every such angle. So theta ranges from pi over 4 to pi over 2, and r ranges from root 2 to 2, with every combination of r and theta within those regions being a point in r. Therefore, we can write the parameters of the integral like this. And this is how a double integral works. if you can write the region you're integrating as basically a rectangle in some coordinate system, meaning one coordinate is ranging over some interval and the other coordinate is ranging over some interval, then you can compute the double integral by integrating with respect to each of these coordinates one at a time, treating the whole double integral as an integral of integrals. In this case, it's actually even simpler than it might be, because the inner function, root 1 plus 4r squared r, is a function only of r. Theta never actually occurs. This allows us to treat this whole thing here, this inner integral, as a constant and pull it out, leaving integral pi over 4 to pi over 2 of d theta, which is simply pi over 2 minus pi over 4 or pi over 4, as it would be if theta were replaced by x. We're taking the integral of 1, right, over the integral from pi over 4 to pi over 2, which simply gives you the length of the interval, or pi over 4. Now, the rest of the integral, which is now a one-variable integral in dr, can thus be calculated using single-variable calculus. The key thing we'll have to do here is a u substitution, which hopefully one is familiar with by now if one has been doing u substitutions. Because what we see here is a quadratic function in r occurring in the first factor. What we have specifically is some function, the square root of a quadratic function of r, and then times r, which is essentially the derivative of any quadratic function. The only possible error will be a constant factor. Specifically, the derivative of 1 plus 4r squared is 2 times 4 times r, or 8r. So if we multiply outside the integral by 1/8, then we can multiply inside by 8 without changing it. And then we have something of the form the square root of a function u times the derivative of u, which allows us to apply u substitution and simplify the integral. Specifically, if we simplify the portion multiplying the integral pi over 4 times 1/8 to pi over 32, we get this. And if we then replace 1 plus 4r squared by u, we can suck up 8r into the differential du and obtain an integral of u to the 1/2, which by the power rule is simply the difference of the evaluations of u to the 3/2 at the boundaries. We have to alter the boundaries during the substitution, of course, letting them now be the values of u rather than the values of the original of r as we had before. And we must multiply by 2/3, as that's the constant required to make 2/3 u to the 3/2 an antiderivative of u to the 1/2. And now evaluating at the endpoints, we end up with pi times 17/48 root 17 minus 9/16, which is as simplified as it can be because the fractions are all simplified, root 17 is irrational, and pi is transcendental. There's no way we can combine pi with the square roots. So it's certainly an ugly answer, but the method has very general applicability. Essentially, to recap, what we did is we analyzed the region R in the xy plane. Then we took a double integral over it of the square root of this relatively simple function of the partial derivatives of the function defining the surface. To calculate the partial derivatives, we looked at the function defining the surface and considered what would happen if we took the derivative of the function as a function of only one of the variables, treating the other variable as a constant. Plugging those values in, we then had a double integral to calculate, which we did by using polar coordinates to obtain the appropriate differential. By using polar coordinates, since we're using polar coordinates, we had to write the differential in polar coordinates and the function itself in polar coordinates. And once we had that, we could calculate the double integral by treating it as an integral of integrals. We saw that since theta wasn't present in the function we were integrating at all, one of the integrals, the outer integral, was easy to calculate. And for the integral, we then had a single variable function that we could quickly evaluate by u substitution in the power rule, giving us our final answer. This method works with all surfaces. Of course, the integrals you end up with may be more complicated, but this method is always going to allow you to reduce the problem to evaluating partial derivatives of the function to find the surface, which is generally not that hard, and subsequently calculating a double integral involving the partial derivatives, which is, in the case of problems you will be assigned by your instructor, usually easy to do either in Cartesian or perhaps more likely polar coordinates. By simply making sure that you express the bounds of the region, the differential, and the function you're integrating itself, which is not the original function z, but this root 1 plus partial z partial x squared plus partial z partial y squared. If you express all of those in terms of the coordinate, whatever coordinates you're using to integrate over the region R, whether x, y, or r theta, then you'll have a valid integral that represents the integral you're trying to calculate according to the formula that I gave. And you can then calculate this one integral at a time, ending up eventually with a single variable integral that will hopefully be amenable to standard methods like substitution or integration by parts. So that's a general method for dealing with surface area. There's so much more to say about where this formula comes from, why this actually works. That's certainly much more interesting than just applying this, but at least this is a formula of broad applicability. And if you understand this method, then you now know how to find the surface area of pretty much anything you can define in 3 dimensions. You may not be able to do all the integrals, but if you use techniques as broad as trig substitution, you pretty much always will be able to do them for any nice surface. And so this is a method that's very broadly useful, even though it might not be clear yet why this works.